Welcome to our exploration of lenses in physics. Lenses are fascinating optical devices that play a crucial role in our daily lives, from eyeglasses to cameras and even telescopes. In this video, we'll dive deep into the world of lenses, uncovering their types, how they work, and their applications. We'll start by understanding what a lens is and why it's so important in the study of light. By the end of this journey, you'll have a clear grasp of the principles that govern lenses and their significance in both science and technology. Let's begin our adventure into the physics of lenses. Lens is a transparent optical component that refracts light to converge or diverge rays. Made typically from glass or plastic, lenses are designed with curved surfaces that bend light in specific ways. This bending of light, known as refraction, is the key to how lenses function. Whether in a microscope or a pair of reading glasses, lenses help us see the world more clearly by focusing or spreading out light. Understanding the basic structure and purpose of a lens sets the foundation for exploring their different types and uses. Fraction is the process by which light changes direction as it passes from one medium to another, such as from air into glass. This change in speed causes the light to bend, and it's this bending that allows lenses to focus or disperse light. The degree of bending depends on the curvature of the lens and the materials involved. Refraction is fundamental to the operation of all lenses, making it a cornerstone concept in optics and physics. Convex lenses, also known as converging lenses, are thicker in the middle than at the edges. They cause parallel rays of light to converge to a single point called the focal point. Convex lenses are commonly used in magnifying glasses, cameras, and corrective eyewear for farsightedness. Their ability to focus light makes them essential in many optical instruments, allowing us to see distant or tiny objects with clarity. Concave lenses, or diverging lenses, are thinner in the middle and thicker at the edges. Unlike convex lenses, they cause parallel rays of light to spread out or diverge. Concave lenses are often used in eyeglasses for nearsightedness and in certain types of cameras and telescopes. Their unique shape and function make them indispensable in correcting vision and manipulating light paths in various devices. Focal point is the spot where light rays converge after passing through a convex lens or appear to diverge from a concave lens. The distance from the center of the lens to this point is called the focal length. Focal length determines how strongly a lens converges or diverges light. Understanding these concepts is crucial for designing optical systems and predicting how images will form. Principal axis is an imaginary straight line that passes through the center of the lens and its two surfaces. It serves as a reference line for measuring distances and angles in lens diagrams. The principal axis helps us understand how light travels through the lens and where images will form. It's a fundamental concept in lens physics and is used in ray diagrams to predict image location. The optical center of a lens is the point through which light passes without being refracted. It's located at the geometric center of the lens. Light rays passing through this point continue in a straight line, making it a key reference in lens diagrams. The optical center is essential for understanding how lenses form images and is often marked in optical instruments for alignment. Ray diagrams are graphical representations used to trace the paths of light through lenses. By drawing a few key rays, we can predict where an image will form and what its characteristics will be. Ray diagrams are invaluable tools in physics, helping students and scientists visualize the behavior of light in optical systems. They simplify complex concepts and make lens analysis more accessible. Convex lenses can form real or virtual images depending on the object's position relative to the focal point. When an object is placed beyond the focal length, a real inverted image is formed on the opposite side of the lens. If the object is within the focal length, the lens produces a virtual, upright image. This property is widely used in cameras, projectors, and magnifying glasses. Concave lenses always form virtual, upright, and reduced images regardless of the object's position. These images appear on the same side of the lens as the object. This characteristic makes concave lenses ideal for correcting nearsightedness and for use in peepholes and certain optical instruments. Their predictable image formation is a key feature in lens design. Real image is formed when light rays actually converge at a point, allowing the image to be projected onto a screen. In contrast, a virtual image occurs when light rays only appear to diverge from a point and cannot be projected. Understanding the difference between real and virtual images is essential for grasping how lenses are used in various devices, from cameras to microscopes. Magnification describes how much larger or smaller an image appears compared to the actual object. It's calculated as the ratio of the image height to the object height. Lenses can magnify or reduce images depending on their type and the object's position. Magnification is a critical concept in designing optical instruments like microscopes and telescopes, where seeing details is essential. Lens formula relates the object distance, image distance, and focal length of a lens. It's expressed as 1f equals 1v 1u, where f is the focal length, v is the image distance, and u is the object distance. This formula is fundamental in optics, allowing us to calculate where an image will form and its size. Mastery of the lens formula is essential for anyone studying physics. Power of a lens measures its ability to converge or diverge light, defined as the reciprocal of the focal length in meters. It's measured in diopters d. A lens with a short focal length has high power, while one with a long focal length has low power. Understanding lens power is crucial for prescribing corrective lenses and designing optical systems. Lenses are widely used in eyeglasses to correct vision problems like nearsightedness and farsightedness. Convex lenses help people with hyperopia farsightedness by converging light onto the retina, while concave lenses assist those with myopia nearsightedness by diverging light. The precise design of these lenses ensures clear vision and comfort for millions of people worldwide. Cameras use lenses to focus light onto a photosensitive surface, such as film or a digital sensor. By adjusting the lens position, cameras can capture sharp images of objects at various distances. The quality and type of lens greatly affect image clarity, depth of field, and overall photographic results. Lenses are at the heart of every camera, from smartphones to professional DSLRs. Microscopes rely on a combination of lenses to magnify tiny objects, allowing us to observe details invisible to the naked eye. The objective lens creates a magnified real image, which is further enlarged by the eyepiece lens. This arrangement enables scientists and students to explore the microscopic world, making discoveries in biology, medicine, and materials science. Telescopes use lenses to gather and focus light from distant objects such as stars and planets. The objective lens collects light and forms an image which is then magnified by the eyepiece. This setup allows astronomers to study the universe in detail, revealing the wonders of space that are otherwise invisible to the naked eye. Projectors use lenses to enlarge and display images onto a screen. The lens system takes a small image and projects it as a much larger version, making it visible to an audience. This technology is widely used in classrooms, theaters, and business presentations, demonstrating the versatility of lenses in modern life. Chromatic aberration is a common lens defect where different colors of light are focused at different points, causing a blurred or colored edge around images. This occurs because lenses refract different wavelengths of light by varying amounts. Lens designers use special materials and combinations of lenses to minimize chromatic aberration and improve image quality. Spherical aberration is another lens defect where light rays passing through the edges of a lens focus at different points than those passing through the center. This leads to a blurred image. Lens makers correct this by using aspheric lenses or combining multiple lens elements, ensuring sharp and clear images in optical devices. Compound lenses are systems made up of two or more simple lenses combined to improve image quality and correct optical defects. By carefully selecting and arranging these lenses, designers can minimize aberrations and achieve desired magnification and clarity. Compound lenses are used in cameras, microscopes, and telescopes for superior performance. Modern lenses often have special coatings to reduce reflections, increase light transmission, and protect against scratches. These coatings enhance image quality by minimizing glare and improving contrast. Lens coatings are especially important in photography, eyewear, and scientific instruments, where clarity and durability are essential. Lenses are typically made from optical glass or high-quality plastics. Glass lenses offer excellent clarity and durability, while plastic lenses are lighter and more impact-resistant. The choice of material affects the lens's performance, weight, and cost. Advances in materials science continue to improve lens quality and expand their applications. Lenses come in various shapes including Biconvex, Plano-Convex, Biconcave, and Plano-Concave. Each shape has unique optical properties suited for specific applications. The design of a lens determines how it bends light and forms images, making it a critical factor in optical engineering. Human eye contains a natural lens that focuses light onto the retina, allowing us to see. This lens changes shape to adjust focus for near or distant objects, a process called accommodation. Understanding the eye's lens helps us appreciate the importance of artificial lenses in correcting vision and enhancing our ability to observe the world. Contact lenses are thin, curved lenses placed directly on the eye's surface to correct vision. Made from soft or rigid materials, they offer an alternative to eyeglasses. Contact lenses use the same optical principles as traditional lenses, providing clear vision and convenience for millions of users worldwide. Fresnel lenses are thin, lightweight lenses made up of concentric rings. They can focus light like a traditional lens but with much less material. Fresnel lenses are used in lighthouses, overhead projectors, and even some vehicle headlights, demonstrating the versatility of lens technology. Zoom lenses allow users to change focal length and magnification without switching lenses. By moving lens elements inside the housing, zoom lenses provide flexibility for photographers and videographers. This adaptability makes them popular in cameras and camcorders, offering convenience and creative control. Wide-angle lenses have short focal lengths, allowing them to capture a broader field of view. They're ideal for landscape photography, architecture, and situations where you want to include more in the frame. The unique perspective of wide-angle lenses can create dramatic and immersive images. Telephoto lenses have long focal lengths, enabling them to magnify distant subjects. They're commonly used in wildlife, sports, and portrait photography. Telephoto lenses bring faraway objects closer, making them essential tools for capturing details that are otherwise out of reach. Macro lenses are designed for close-up photography, allowing detailed images of small subjects like insects and flowers. They have a short minimum focusing distance and high magnification, making them perfect for capturing the intricate beauty of the microscopic world. Astigmatism is an optical defect where a lens fails to focus light evenly, causing blurred or distorted images. This can occur in both natural and artificial lenses. Specially designed corrective lenses can compensate for astigmatism, restoring clear vision and accurate image formation. Manufacturing lenses involves precise shaping, polishing, and coating of optical materials. Advanced techniques ensure high accuracy and quality, meeting the demands of modern optical devices. The process combines traditional craftsmanship with cutting-edge technology, resulting in lenses that power everything from smartphones to scientific instruments. After manufacturing, lenses undergo rigorous testing to ensure they meet optical standards. Quality control checks for defects, clarity, and performance. Only lenses that pass these tests are used in high-quality optical devices, guaranteeing reliability and excellence in every application. Recent innovations in lens technology include adaptive lenses that change shape electronically, lightweight materials, and advanced coatings. These breakthroughs enhance performance, durability, and versatility, opening new possibilities in photography, medicine, and scientific research. Virtual reality headsets use specialized lenses to create immersive 3D experiences. These lenses focus and shape images for each eye, simulating depth and perspective. The design and quality of VR lenses are critical for comfort and realism, making them a key component in the growing field of virtual reality. Augmented reality devices use transparent lenses to overlay digital information onto the real world. These lenses must balance clarity, brightness, and field of view to provide seamless integration of virtual and physical environments. AR lenses are revolutionizing how we interact with information and our surroundings. Lenses are essential in laser technology, focusing and directing laser beams for applications in medicine, industry, and research. Precision lenses ensure that laser light is accurately delivered, enabling procedures like eye surgery, cutting materials, and scientific experiments. Fiber optic systems use tiny lenses to couple light into and out of optical fibers. These lenses ensure efficient transmission of data over long distances, forming the backbone of modern communication networks. Advances in lens design continue to improve the speed and reliability of fiber optic technology. Beyond scientific instruments, lenses are found in everyday objects like magnifying glasses, binoculars, and even smartphone cameras. Their ability to manipulate light makes them indispensable in modern life, enhancing our vision, entertainment, and ability to explore the world. The future of lens technology promises even more exciting developments, from smart lenses that monitor health to ultra-thin lenses for wearable devices. As research continues, lenses will become more powerful, versatile, and integrated into our lives, shaping the way we see and interact with the world. We've covered the essential concepts of lenses in physics, from their structure and types to their applications and innovations. Understanding how lenses work helps us appreciate their impact on science, technology, and everyday life. Whether correcting vision, exploring the universe, or advancing technology, lenses are truly remarkable tools. As we conclude our journey through the world of lenses in physics, take a moment to reflect on how these simple yet powerful devices shape our understanding and experience of light. From ancient magnifiers to cutting-edge smart lenses, the evolution of lens technology continues to inspire innovation and discovery. Thank you for joining us on this enlightening exploration.